Hello, everyone. I am Ying from the Beijing Institute of Technology. Today, I am delighted to share our team's recent work titled Quasi-Synchronous Random Access for Massive MIMO-Based LEO Satellite Constellations. This paper has recently been accepted by IEEE JSAC, and you can find the source code available on GitHub. For further information, please visit our group's homepage, which is linked below. Today's presentation consists of 6 sections: Introduction, Preliminaries, Massive Access Processing at Single Satellites, Massive Access Processing based on Multi-Satellite Cooperation, Simulation Results, and Conclusion. The development of LEO satellite constellations has opened up numerous opportunities for achieving seamless space-air-ground integrated connectivity. In particular, given the extensive coverage required for machine-type communication, MTC, devices and the growing demand for increased transmission bandwidth, there is a significant interest in advancing broadband LEO satellite-enabled non-terrestrial networks, NTNs, as an integral part of our communication infrastructure. Now, let's delve into our research. We are focusing on the massive access scenario for MTC, where a vast number of potential MTC devices are involved. In this context, only a small fraction of these devices are randomly activated by environmental events, and they need to upload corresponding data packets. In such a massive random access problem, using conventional grant-based access protocols becomes inefficient. These protocols require multiple handshakes between user terminals and the base station before establishing a transmission link. This can lead to significant access latency due to the long propagation delay. In contrast, grant-free access protocols enable active user terminals, UTs, to transmit data packets directly over the same channel without needing permission from the base station. This approach significantly reduces access delay. However, because all data packets are superimposed at the receiver, specialized signal processing mechanisms are necessary to address key challenges such as channel estimation, CE, activity detection, AD, and data detection, DD. To accommodate the varying signal processing capabilities of satellites, we have developed 3 access frameworks: Single Satellite Non-Cooperative Processing, SSNCP, Multi-Satellite Cooperative Terrestrial Processing, MSCTP, and Multi-Satellite Cooperative Onboard Processing, MSCBP. Now, let's take a closer look at the 3 access frameworks: SSNCP, MSCTP, and MSCBP. In SSNCP, we assume that the computation ability of the satellite is powerful enough to independently handle the tasks of CE, AD, and DD. In MSCTP, we consider satellites with limited computation ability. Here, the simple tasks of CE and AD can be performed on the satellites, given their time-sensitive nature. The more complex DD task is solved by a terrestrial central node with the assistance of a backhaul link. In the case of MSCBP, we envision a heterogeneous satellite constellation, where a specific satellite with high computation power acts as an onboard central node. As shown in Table I, different frameworks may encounter distinct practical challenges when performing various tasks. For the CE problem, since it is a satellite-independent task, each satellite must address it independently. For the AD task, the terrestrial satellite link, TSL, between a single UT and a satellite may deteriorate in some scenarios. Therefore, centralized processing with cooperation in both MSCTP and MSCBP may enhance AD performance. Regarding the DD task, due to the spatial correlation of channels, active UTs sharing the same time-frequency resources and located in neighboring direction may be challenging to distinguish for a single satellite. This could lead to performance degradation in SSNCP. However, MSCTP and MSCBP can provide multiple observations of the UTs, potentially mitigating this issue. When we further consider the differences in backhaul links, we'll delve into the slight distinctions between MSCTP and MSCBP, which we'll illustrate in the later part of our presentation. Let's delve into MSCTP as an example and explore the challenges and solutions for CE, AD, and DD problems in LEO constellation-based random access. We have taken into account the following channel features and have proposed corresponding strategies. 1. Handling quasi-synchronous data arrival. To address the issue of imperfect synchronization caused by different time of arrival from different active UTs, we have introduced a training sequence padded multi-subcarrier system, TSP-MCS, frame structure which can overcome the issue of imperfect synchronization. 2. Managing structured TSL channels. For structured TSL channels, we employ the orthogonal approximate message passing multiple measurement vector, OAMP-MMV, algorithm. This approach enables us to perform joint activity detection and channel estimation, JADS. To further harness the potential of the receive array structure, we employ a 2D Esprit technique to enhance channel estimation. 3. Addressing quality-constrained and correlated TSLs, we have introduced a majority voting scheme to enhance activity detection in cases with quality-constrained and correlated TSLs. Additionally, when faced with correlated channels among active UTs, we have developed multiple satellite cooperation DD algorithms to ensure robust DD performance. We consider the random access within the MSTBP framework, as illustrated in Figure 4. In this scenario, we assume that QLEO satellites are simultaneously providing access services to KUTs within the same coverage area. Each satellite is equipped with a uniform planar array, UPA, consisting of NR antenna elements. The target UTs can access to the satellite network via very small aperture terminals, SATs. For the more advanced SATs, we consider the adoption of phased array antennas with multi-stream beamforming capabilities. Therefore, we assume that each UT is equipped with Q radio frequency, RF, chains and NT antennas to facilitate multi-stream beamforming. The same data packets are transmitted through different RF chains to harness diversity gain. In a specific coherence time interval, only Ka UTs out of the total K potential UTs are active, in line with the sporadic traffic characteristics often observed in MTC. Our approach involves aligning each RF chain's data stream with a specific satellite through beamforming. This allows us to express the equivalent channel between the KTH-UT's QTH RF chain and the QTH satellite using equation 1. In this equation, alpha K serves as the activity indicator, taking the value of 1 when a UT is active and 0 otherwise. Beta represents the equivalent complex channel gain, while AR denotes the antenna steering vector at the receiving end. It's worth noting that we've leveraged the unique properties of TSLs, where nearly all multipath components at the satellite have almost the same angle of arrival, AOA. When we stack over all L taps of G, K, Q, in the delay domain, we obtain the overall channel impulse response matrix H, K, Q, which can be expressed as the outer product of the channel impulse response H, K, Q, and the steering vector AR. Let's explore the entire transmission procedure, which is illustrated in Figure 5. To achieve a low peak-to-average power ratio, we employ a discrete Fourier transform spread orthogonal frequency division multiplexing, DFTSOFDM, waveform to assemble the data block X. Before forming the data block X, we introduce a known pseudonoise training sequence, TS-C, which is padded before X to create a complete frame S in the time domain. Before transmitting the source packets to different target LEO satellites, we duplicate the TSP frame into multiple copies. Each stream then undergoes individual timing advance and power control to ensure balanced received energy at the receiver. Additionally, we assume that Doppler compensation has been carried out at the transmitter, and the residual Doppler effects are minimal. Next, analog beamforming is independently performed at each RF chain to generate a directional beam for each LEO satellite. Specifically, for the QTH satellite, the received signal at the JTH antenna from the KTH user is the convolution between the QTH transmit stream S, K, Q, and the corresponding channel impulse response vector. Here, S, K, Q represents the data stream from the KTH-UT's QTH-RF chain, with each frame composed of a length MTSC and a length N data block X. Summing up the signals from all the UTs, we obtain the received signal stream Y, Q, J, as described in equation 3. Based on the received signals, the receiver edge satellite's nodes and central node needs to estimate the active user set, AUS, and corresponding channel impulse response, CIR, matrix, and then demodulate the information bits. Now, let's proceed with massive access processing at a single satellite. Moving on, we begin by formulating the JADS at each satellite node as a compressed sensing problem, using the OAMPM-MV algorithm for estimating the CIR and AUS. As illustrated in Figure 6, our specially designed TSP-MCS system allows for a maximum relative channel delay, RCD, of LTS. A TS of length M, longer than L, provides a small non-inter-symbol interference, ISI, region of length G equals M-L plus 1 at the receiver, which can be utilized for JADS. In this non-ISI region, by converting the convolution operation into matrix multiplication, the received signal at the JTH antenna from all the UTs can be rewritten as the sum of the product of all user-specific TS psi k and corresponding CIR matrix H, K, Q, as shown in equation 4. Here, psi k is a known Toeplitz matrix. By stacking all the TS matrix and CIR matrix, the received TS in the non-ISI region can be rewritten as equation 6. Here, all the columns of H, Q tilde share the same support set due to the same sparsity of its activity and delay domain CIR at different antennas. Since equation 6 is a typical compressed sensing problem, we first consider the sparse recovery problem for each column independently. For notation simplicity, we simplify the observation model into the form of Yj equals psi Hj plus Nj, which can be efficiently solved by the OAMP algorithm. The optimal OAMP structure with a single measurement vector in the IOTA-TH iteration for such a problem is given by the iteration between linear estimator in equation 8a and nonlinear estimator in equation 8b. Assuming a Bernoulli-Gaussian prior distribution for each channel element, we can derive the posterior mean and variance of the minimum mean square error, MMSE, estimator phi iota hat in the nonlinear estimator module, as shown in equation 10 and equation 11. When substituting Hj with each column of Hq, the channel estimation problem can be solved column by column. However, it's important to note that the hyperparameters in the prior assumption are unknown during nonlinear estimation. Additionally, the spatial common support property for different receive antennas as presented in equation 7 is not taken into account. To address the previously mentioned issues, we introduce an approach that partially leverages the common support property while updating hyperparameters through the expectation maximization (EM) algorithm. Let's denote the unknown prior parameters as theta, and the EM algorithm consists of two crucial steps. In the E step, we calculate the expectation of the logarithmic joint distribution P, H, Y, where this expectation is computed over the conditional distribution P, H, given Y. This conditional distribution can be obtained in the preceding OAMP procedure. In the M step, we the derivative of the Q function with respect to the hyperparameters to determine the values of theta that maximize Q. By executing these two steps alternately throughout the entire iteration process, we can estimate the unknown hyperparameters. Furthermore, given that all antennas receive signals simultaneously, it is reasonable to assign a common activity indicator for each row in HQ. This common activity indicator signifies that a refined activity indicator can be determined using equation 14. Considering that the row dimension of HQ encompasses both UT activity and the delay domain channel, we initially identify the support set of HQ using an energy-based detector. For a specific row, if the energy of each element exceeds a given threshold, it is considered a positive estimation. When the ratio of positive estimations surpasses a certain threshold, this row is deemed active. By accumulating the support sets across continuous L taps for a specific UT, we can establish the active user set, as shown in equation 16. Since the iteration between the EM and OAMP can collectively leverage the common support property across different columns, we refer to the entire algorithm as the OAMP-MMV algorithm. While the common activity property has been integrated into the OAMP-MMV algorithm, the spatial structure of the TSL channel is still not fully considered. To address this, we employ a parameterized channel estimation method based on the 2D Esprit algorithm. The fundamental concept behind parameterized CE is that the TSL channel can be defined by some key parameters, such as AOA, delay, and channel gain. Given that an initial estimate has already been obtained, we can enhance CE by further leveraging the channel structure. In this process, we first estimate the AOA for each active UT. Let Sk denote the set of non-zero row indices corresponding to the KTH-UT's channel, and we can represent the equivalent observations for the KTH-UT's channel as xk tilde. Then, we efficiently estimate the AOA for UTK using the 2D Esprit algorithm. In the second step, since the initial estimation of each path has been obtained by OAMP-MMV, and the channel for each path is simply the product of channel gain and the corresponding steering vector, we can readily acquire the estimation of channel gain using the least squares method. By combining the estimated AOA, channel gain, and known channel delay from the OAMP-MMV algorithm, we can reconstruct the original channel as a whole. As this reconstruction process utilizes prior information about the antenna array structure, it leads to an improved channel estimation performance. Now, let's delve into the data detection problem in the single satellite case. As depicted in Figure 6, the received data segment is affected by training sequence from neighboring frames. To facilitate data detection, we initially construct a local frame for the KTH-UT. This local frame contains the TS part and an empty data part and is denoted as SKO. Subsequently, by simulating the transmission progress at the receiver, we obtain the received frame as the convolution of SKO and the estimated channel impulse response HKQ. By summing over all the estimated active UTs, we can calculate the received frame at the JTH antenna, as described in equation 19. This approach allows us to subtract the contamination introduced by the TS from the actual observations, improving the accuracy of our data detection. Finally, we transform the data and corresponding channel into the frequency domain, enabling us to address the subcarrier-wise data detection (DD) problem, as shown in equation 23. This overdetermined problem in equation 23 can be efficiently solved using the least squares method. Afterward, following subcarrier mapping in the inverse discrete Fourier transform (IDFT), we successfully recover the original data symbols in the DFT-SOFDM system. In the previous sections, we presented solutions for the joint activity detection and channel estimation and data detection problems in a single satellite-enabled massive access system. However, the performance of activity detection and data detection is influenced by the conditions of TSLs. To be specific, AD performance is impacted by the quality of TSLs, while DD performance is influenced by the channel correlation among active UTs. Regarding AD, the estimation of the AUS may encounter issues like missed detection or false alarms. The algorithms discussed earlier provide an initial estimate of the AUS at each satellite independently. In our diversity transmission scheme, active UTs simultaneously transmit identical data packets to the target satellites, and the detected AUS should be consistent across all received satellites. To mitigate errors from individual satellite detections, we employ a majority voting method to determine a reliable AUS by aggregating data at the central node, as demonstrated in equation 25. For the DD problem, as the number of UTs increases, the likelihood of high spatial correlation between adjacent UTs channel vectors also rises. This can result in a rank deficiency of the channel matrix and lead to degraded bit error rate (BER) performance. The spatial correlation, often caused by geographical similarity, can be addressed from two perspectives. The first approach involves introducing a sufficiently large angular difference in space. For instance, as shown in Figure 7, UT1 and UT2 exhibit similar AOAs when transmitting information to Satellite 1. By introducing an additional satellite, such as Satellite 2, we can observe a greater angular difference, which aids in suppressing spatial domain inter-user interference. The second method leverages the diversity of channel gain. For example, when UT1 and UT3 share similar AOAs for all the satellites, diversity gain can help reduce spatial correlation in this scenario. To offer a clearer understanding, let's consider a simple scenario involving two UTs. These UTs are geographically close to each other and are equipped with uniform linear arrays. They are simultaneously served by Q satellites. The overall channel matrix is represented as equation 26. We denote the column correlation between two columns as C0, and we have plotted the cumulative distribution function, CDF, of C0 based on 5,000 Monte Carlo simulations. The results indicate that increasing the number of satellites can reduce channel correlation, even for small angular differences. As a result, the central server node can aggregate data from multiple edge satellite nodes and stack them to formulate the following cooperative data detection problem in equation 27. This approach effectively addresses the challenge of channel correlation in data detection. The multi-satellite cooperative linear data detection algorithm in equation 27 assumes a perfect backhaul of observations, denoted as from edge nodes to the central node. This requirement necessitates high-capacity backhaul links. To address this, we delve into the scenario of quantized backhaul. Taking the MSCBP as an example, the central node can retain its local unquantized observations received from terrestrial UTs. For the edge nodes, only quantized frequency domain observations and channel impulse response matrices are fed back to the central node before it carries out DD. Consequently, the centralized DD problem becomes a mixed resolution problem. As presented in equation 28, for the central node, its primary task is to recover the x, n, from the estimated h n and the quantized observation z, n. More specifically, we denote RC as the set of row indices corresponding to the central node and RE as the set of row indices corresponding to edge nodes. The quantization function is depicted in equation 29, where Q_B represents a b-bit complex quantizer capable of quantizing the real and imaginary parts of the input separately. We propose a multi-satellite cooperative Bayesian dequantization DD algorithm to tackle the aforementioned problem. As shown in Figure 9, the proposed iterative algorithm comprises 3 modules. Module A performs posterior estimation of the unquantized observation YPN based on the prior information YAN and the quantized result ZN. Module B estimates the original data symbol XN using a linear minimum mean square error (LMSE) estimator. In Module C, the prior constellation information of data symbols is leveraged to refine the estimation results. All 3 modules operate iteratively until convergence is achieved. In Module A, the estimation process of unquantized observation is described by equation 30. Moving on to Module B, it obtains the posterior estimate of the frequency domain information, denoted as XPN, and the corresponding variance sigma XP, based on the prior information and the dequantized observation YPN obtained from Module A. In Module C, considering that the data symbol is carried in the time domain for the DFTSOFDM waveform, the frequency estimation results are initially transformed into the time domain, as shown in equation 33. Utilizing the concept of variational Bayesian methods, we can derive the posterior distribution of each data symbol from the joint distribution. By taking expectations over other irrelevant variables and simplifying the expression, we can calculate the posterior distribution of each data symbol, as presented in equation 35. Subsequently, the posterior mean and variance of x, t, m, can be obtained based on the maximum a posteriori criterion. The prior information that needs to be passed to Module A and Module B can then be updated accordingly. The overall data detection procedure involves the iterative execution of Module A, B, C. For the MSCTP case, where high-resolution observation data cannot be acquired, the above algorithm can still be applied by simply modifying the index sets RC and RE. In the next, we conduct simulations to validate the superiority of our proposed schemes. Some key simulation parameters are listed in Table 2, which includes the number of satellites, number of potential UTs, data size for each frame, number of antennas at the satellite, and the maximum relative channel delay. The performance evaluation metrics for AD, CE, and DD are defined as user activity error probability, AEP, normalized mean square error, NMSE, and bit error rate, BER, given respectively as equation 37. Now, let's examine the results presented in Figure 10, where we compare the performance of our proposed schemes with benchmark algorithms. The figure illustrates the NMSE, AEP, and BER as functions of the non-intersymbol interference, ISI, region length G achieved by various algorithms. For this simulation, we set the signal-to-noise ratio to 12 dB, the number of active UTs to Ka equals 15, and each TSL comprises P equals 3 paths. In the figure, the simultaneous orthogonal matching pursuit, SOMP, algorithm represents a classical greedy search-based compressed sensing algorithm. The Oracle LS assumed the support set of the channel matrix to be known, and then perform LS for channel estimation. ALG1 foot means that only OAMPMMV algorithm is executed at the satellite node when performing CE, while ALG1 plus ALG2 stands for the enhancement of 2D Esprit-based parameterized CE applied after the original OAMPMMV algorithm. Regarding CE performance, OAMPMMV leverages the common sparsity property among different antennas, achieving good performance when the non-ISI region is sufficiently large. Furthermore, the high-resolution 2D Esprit algorithm, which accurately captures angle information, significantly improves channel estimation performance. For AEP performance, our proposed methods outperform SOMP in both non-cooperative and cooperative processing. Additionally, cooperative processing significantly enhances AEP performance over non-cooperative processing. This improvement arises because if one LEO satellite misjudges the active state of a UT due to unfavorable channel conditions, observations from other LEO satellites can largely correct this error. In the BER performance comparison presented in Figure 10c, we also include the idealized perfect CSI case. Non-cooperative processing represents single satellite data detection without considering channel correlation among active UTs, leading to poor BER performance. Our cooperative processing mitigates the adverse effects of high channel correlation, and the proposed ALG1 plus ALG2 achieves superior BER performance compared to other schemes, thanks to a more accurate CE result. In Figure 11, we examine the performance metrics as functions of the number of active user terminals under various algorithms. Similar to previous results, our proposed ALG1 plus ALG2 achieves the best channel estimation performance. Moreover, cooperative processing significantly enhances the AEP and BER performance compared to non-cooperative processing. In Figure 12, we compare the proposed Bayesian dequantization data detection algorithm with the simple least squares method in the quantized backhaul case. For both MSCTP and MSCBP, our proposed method achieves the best BER performance. This implies that, for a target BER, our proposed scheme can use much shorter training sequences than LS, reducing transmission delay. Additionally, the proposed scheme in the MSCBP case exhibits the smallest BER gap compared to the perfect backhaul case, demonstrating the effectiveness of our proposed scheme. Figure 13 investigates the influence of quantization resolution on BER. As quantization resolution improves, the BER gap between MSCTP, MSCBP, and the perfect backhaul becomes smaller. Figure 16 explores the impact of receiver antenna size and channel coding on DD performance. In low-resolution cases, such as 2-bit quantization backhaul, increasing the antenna size and adding channel coding can significantly enhance DD performance. Finally, we conclude our work. The random access problem in MIMO-based satellite communication systems has been investigated in this paper. Specifically, we have constructed a multi-satellite system where a TS is utilized to perform JATs at edge satellite nodes. Exploiting the sparse feature of TSLs and sporadic transmission of its traffic, our system acquires an initial estimate through the OAMP-MMV algorithm, after which a 2D Esprit method is applied for enhanced parameterized CE. Moreover, we have proposed a majority voting method to enhance AD performance by aggregating information from multiple edge nodes. To deal with the high spatial correlation among its channels, a multi-satellite cooperative linear DD algorithm and a multi-satellite cooperative Bayes dequantization DD algorithm have been proposed for perfect backhaul and quantized backhaul, respectively. Simulation results have verified the effectiveness of our proposed scheme in terms of CE, AD, and DD performance for quasi-synchronous random access satellite systems. One deficiency of the proposed scheme is that it is limited to the case where the total number of potential UTs is fixed, and it cannot adapt to the variation of newly enrolled or exited UTs. A more practical solution is to investigate unsourced multiple access methods in hybrid MIMO-based LEO satellite constellations. Here are some main references for the slides. To find more information about this work, please refer to the original article below the video. Thanks for your attention.